Okay, so this is a test review for the upcoming tests on torque, center of mass, all that. So our first question asks, we have to find the center of mass of this object here. So it is on an XY Cartesian plane, and we can first locate the center of mass for all of these individual blocks, which are obviously going to be right in the center. So that is where we're looking, right? And so what we have to do is we separate this into the X and the Y, and we can kind of like sum them up pretty much. So what do? Let's go to X. So in the X, which is going to be vertical lines, we have to count how many red dots there are on each side. So in the negative 0.5, right, because this whole jump would be 1, so this to the center is negative 0.5. So negative 0.5 times however many dots there are on this negative 0.5 line. So how many are there? 1, 2, 3. So there's 3 out of how many in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of 10. Then add that, and you just keep going. How many? So let's see, this is on the positive 0.5. So 0.5 times 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 out of 10. Continue this process, and you get positive 1.5 times, how many are there? 1, 2. 2 out of 10. And you can pretty much put this in the calculator, and you should get a positive 0.4. And then we can separate into the Y coordinate, and these are going to be horizontal lines where the reds are. So we can start at the bottom here. So what are we at? So this is negative 0.5, negative 1.5, negative 2.5, right? Negative 2.5 times how many are there? 1, 2, 3. So 3 out of 10. And then continue. Next one, negative 1.5 times 1 out of 10 plus negative 0.5 times 2 out of 10 plus positive 0.5 times 2 out of 10, and finally plus positive 1.5 times 2 out of 10. And you should come out to negative 0.6. Negative 0.6. So if it asks what is the center in, like, we would go plus 0.4 comma minus 0.6. And we can even kind of look for that. So plus 0.4 in the X would be around this red dot here, and minus 6 would go down a little bit. So it would be around right here. And that is how to do a center of mass problem like that. Okay, our next one is a bar with 2 pivots, and it is pretty much asking what is the force of A and the force of B. So what do we have to know? Well, we know the RF sine theta, but sine theta, the theta is 90 here, so it's just RF pretty much. Those are our torques. So we can do torque, or tau. It's going to be our R, right? So we're going to start with this to the center, right? So this fulcrum or pivot, whatever, to the center. And we know that the length is 1.2, so this whole thing is going to be 0.6. So 0.6 minus 0.3, what is this distance? It's also 0.3. So 0.30. And then RF. So what is the F? Well, it is the mass of the bar times gravity. So 0.3 times 1.50 times 9.81. And then it would be sine 90, but we don't need that because that's just 1. Then that is going to equate to the distance from FA fulcrum to FB pivot, whatever. And what is that? Well, we can just do simple math. If this is 0.3, so 0.6 plus 0.5, so 0.75. So that's what that's going to be, right? Our R, which is, right, FB to this whole thing, that is going to be our R. That is 0.75. Just found that. And that is going to be times the F. Well, what is the F? Well, the F is FB, this force right here, right? So once we have that, we can do a numeric solver, and we can find out to be FB equals 5.89 newtons. So that is how to find FB. Now, how do we find FA? Well, if we think about it, the bar coming down, from the mg, right? That force right here, this is mg, and that is going to be equal the force of A pushing up and the force of B pushing up. So these two forces added are going to cancel out this one force coming down. So what can we do? We can do FA plus FB, which is, we just found, 5.89, is going to equal mg, 1.50, right? That's the mass, times 9.81. And we can use solver, and we can get FA equals 8.83 newtons. And that is how to do a bar and pivot question like that. Okay, the next question is like a bar and a tension wire holding the bar, and there's a mass hanging off of it. So this one is kind of tricky, but it's doable. So the first thing you want to do is pretty much set all your like the net torque, and it's going to cancel out. So what torques do we have? Well, we have this, the bar, the gravity of the bar is bringing it down. The mass of here is bringing this down. So those are two things, and that's being canceled out by the tension right here, and which is going counterclockwise. So clockwise, clockwise, counterclockwise, and they all have to cancel out. So what can we do? We can set up our clockwise forces. So we can start with the bar. So we go RF sine theta. What is the R? Well, it is to the middle, right? So what is the middle? It's 2.88 divided by 2, 2.88 divided by 2. R and the F, well, what is the F? It's going to be mg, so mass of bar is 12.4 times 9.81. And then we have sine theta. This is the tricky part. So our theta, how do we find our theta? Well, the best method to do this is you go from where the R is and where the force is, and that will form an angle, and that is your angle. So what is the angle for the this one right here? Well, follow the R. So it's going to be all the way up until the center. And then what is the force, and which direction is it going? Well, it's mg, it's going down. So it's going to go like that. So blown up, this is going to look like, here's the bar and the force, this is halfway, right? This is 1.44 distance, and it's going to be going down. So that is this angle right here. What is that angle? Well, it's going to be, we can kind of draw our own invisible line right here, right? And that'll form a 90-degree angle. So I'll blow this up. So this is what, boom, that's the 32.5. This forms a 90 degree. So what can we do? Well, 90 minus that, and that gets us our angle, which is 57.5. So that is how to do the theta, right? That is one of the clockwise motions. Then we add that with another clockwise motion, which is this mass hanging off. So same thing, R, F, so R, what is the R? Well, it's 2.88 minus 0.28, because it's that distance. So that is the R all the way up until this line, right? That's R. Our F is mg, 29.2 times 9.81. Now we have to do our sine theta, which is also, in this case, going to be the same thing, because it's just pretty much further back, but it's the same. So it's going to look like this, but our R is just more. And so this is, and it does this. So that's just going to be the exact same angle, which is 57.5. Now that is going to equate to the tension counterclockwise torque. So what is that? Well, it is the R F sine theta. So our R is this distance given, right? It's from the, what's it called? Hinge, from the hinge to where the tension locks on with the bar. So that is 1.3 given 1.30. That is R. What is F? F is T, tension. And then it's going to be sine theta. What is sine? So let's think about this one. It is R, right? Then follow the force, which is tension, which goes up. So it's going to be boom and boom. So it is this big angle here, right? So what is that? Well, let's blow this up again. So it looks like 1.3, right? That's 1.30. And tension goes like that. So it's that angle. And we are given that if we expand the bar more, we are given that this is 111. So that means, right, geometry, this thing forms a 180 degree, right? That's 180. So 111 minus 180, and you get 69. 69. Boom. Now you can use numeric solver, solve for T, and you should get T equals 639 newtons. Now, what do you do from there? By the way, sorry, what we're solving for is the force on the hinge in the x and y direction. So we get our tension, right? Now we can solve for force hinge x. So how do you do that? That's pretty easy. It's force hx to indicate force hinge in the x direction equals, it's our t sine theta, or t, and you have to find the angle. So our t is 639. Now, what can we do? Well, we have to think about this. The force on the hinge is, let's blow it up again. So it looks like this, that's the bar, that's the tension, right? And this is the wall. So this is 111, and we found out this was 69, and we can cut this in half to form a 90-degree angle right here. And we also know that this is 32.5. So that would mean this angle right here would have to be, what, 57.5? Because that comes up to a 90-degree angle, right? That's what that is. So if you add those, that's 90, right? This forms another 90, so 90 minus 57.5. So yeah, you get 32.5, and then to find this small angle right here, because that's what we're solving for, we can do 69 minus 32.5, and we should get 36.5. So we can do 36.5, right? So 90 plus 36.5, 80 minus that, and you get 53.5 for this angle. So we just solved for all the angles, kind of not really necessary. You just need this 36.5 or 53.5 angle right there, and then you can pretty much solve for the x direction. So we can either do sine of 53.5 to get this, or we can do cosine of 36.5. Either way is fine. I just did both just to show that you can do either way. So we'll just do sine 53.5, and our FHX should come out to 514 newtons. Boom. Now, how do we find FHY? Well, FHY, it's a big H, sorry, is going to be, well, think about it. What two things are going up, right? So we have the force on the hinge, which is going up. And what do we also have? We have the tension force that is bringing it up as well. And that is counteracted by the mg's of the mass that is hanging off, and as well as the bar mg. So FHY plus the tension, right? So that is 639, and we can just flip it to find this one, right? It was 53.5 sine to find the x. Now it's 53.5 cosine to find the y. So cosine 53.5, and that is going to equal our masses combined, which is going to be 29.2 plus 12.4 times 9.81. Now you can numeric solver, and you should get FHY equal out to 28.0 Newton. And that is how to solve a question like that. Okay, the next question is a ladder problem. And before we start, just want to shout out Kunling Wu for helping in this problem. So, all right, well, what do we do here? Well, we have a ladder and we have a person here, and they are 3 meters away from this central point here. And the whole length of the ladder is 3.5 meters, and the weight, blah, 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 all that. So what do we do? Well, we should first write out the forces that are on this entire system here that will keep it at equilibrium. So what do we have? Well, we have our forces going downward, right? So what is that? That is going to be the ladder going down, which is mg, right? And we also have the person that is bringing these down, which is also mg. So we have those two downward forces. Then what upward forces do we have? Well, we have this ladder that is being pushed into the ground, right? So what is an equal and opposite force? It is going to be the normal force that is going to push it up. So what can we call that? We can call the normal force of the floor. Then we have the ladder that is wanting to drag downward, right? So what is keeping it up? It is friction. So the upward force is the force of friction on the wall, which we can use W for wall. Then we have horizontal forces or x direction forces. What are those? Well, we know that the wall is being, the ladder is being pushed into the wall, so equal opposite is the normal force pushing it back, so the force of the wall, right? And then we have the other horizontal force, which is the ladder is wanting to go left, but friction is keeping it right, so it is going to be right, and that is the force of friction on the floor. So now that we have 6 forces, we can set those up into linear and rotational forces. So first we can do our linear. So what do we have? Well, first let's do the x direction, so that's really easy. Force of the friction of the floor is going to cancel out with the normal force of the wall. Now we can simplify this even more because we know the force of friction on this on the floor here, which is 0.180, that's the coefficient, times the normal force. So what can we change this to? We can do 0.180 times our normal force, right? So that is the force of friction. That is the normal force right here. Is going to equal the normal force on the wall going that way. So that is one equation that we have, right? Then our next one is going to be canceling out the y direction linear forces. So we have the force of the floor plus, we can do the same thing here. We have, well, let's do our up direction ones. So force mu of the wall is also an up direction one. So force mu of wall is going to cancel out with the mg's, right? So these two combined. So let's just combine their masses. So 65.7 plus 6.50 times 9.81. And we can simplify this even more like we did in this one. So force of mu of the wall, well, we have 0.250. So force of floor plus 0.250 times the normal force of the wall is equal to, this simplifies to 708. Now, what can we do? Well, we can do a simple substitution. We can substitute this FW for 0.180 F force of the floor. So once you do that substitution, which I'm sure you know how to do, right? Just put this in there. You get your force on the wall as 122 newtons and the force of the floor as 678 newtons. Now, once you've done that, you can do your rotational forces, set all those up. Okay, so how do we do that? Well, it's RF sine theta, right? So we can start with the forces going clockwise, right? So going down, which we have as RF sine theta. So we can start with the bar. The R is going to be to the center of mass, so half of 3.5, which is 1.75, times force, which is 6.50 times 9.81 sine. So what is our theta here? Well, like I said in the thing, it goes from your R to the force. Well, what is it? So blown up, this looks like R, and what's the force? Boom. And we know that this is theta. So what is this angle? That's what we're finding, which is 90 minus theta, right? Simple. Plus the other force going down on the person. So that is length to the person, which is 3 times, that is R. What is our F? 65.7 times 9.81. And like the other one, it's extended and going down. What is that? It's the exact same angle. So sine 90 minus theta. And that is equal to these forces here, the force of friction on the wall and the force of the wall normal force. So what do? Well, we do the full distance, the R, which is 3.50, times, well, what is it? Well, we're finding the force here, right? So RF sine theta. So what is the force? Well, it is 0.250 times the force on the wall, right? That is the normal force to find, the force. So force on the wall is 122. That's what we solved for. And that is sine our theta. What is theta here? Well, if we're finding here, we can blow this up once again. It goes like this. Here's the wall. So the force that we're finding here for this one, right? It goes like the R, 3.5, and what does it follow? The force, which goes up. So you're finding this big angle right here. So what do? Well, we know that this is theta, and this is 90, and it looks like this, right? So this makes a 90-degree angle, and we know that this is theta due to alternate interior angles. So we can do 90, right? That's what this is, plus theta to find this big angle. So 90 plus theta, and that we are going to add that with the other rotational force, which is, the force of the wall. So what is that? It is, once again, R, which is the full length, 3.50, times the force on the wall, right? We have that, which is, we solved for, 122. And that is going to be sine of theta. Well, what is theta? Well, let's do it. Let's blow it up again. We have our R, and it looks like this. That is the direction. So what angle? It is this angle. And once again, what is that angle? Well, we solved it here. It is theta. So sine theta. Now, what we do, we just numeric solver, and you get theta equals 77.6 degrees. That is the minimum theta to keep this wall and ladder and person at equilibrium. And that is how to do a question like that.